I will finish that problem in another.
Okay, so
Okay, can you guys read that?
yeah.
Okay. So go ahead and bring us
Go
through
ahead and
it.
start it off. Okay, so Spider-Man decided to cook for Mary Jane, and he had no little cartridges to get the garlic powder from the top. He didn't want to climb because the cabinets would be in the way, and I don't know, he didn't want to jump, hit a sore muscle. So he had to stand on his tippy toes to reach the garlic powder. What was the, okay. What is the force extended by the Achilles tendon when he stands on his tippy toes? So the normal force applied by the ground on his toes was 550. The distance from his, can I zoom in on this?
Yeah, go ahead.
Cool. Did you draw that
I
in?
did.
That's cool.
I'm artistic. Okay, so you can see that the normal force is here on his toes. The distance from his toes to the joint is 95 millimeters. And the distance from the joint to the point on the tendon is 75 millimeters. And the tendon's going at a 88-degree angle, yeah. And then the height from the ground to the ankle is 175 millimeters.
Huh.
So what is the force on the tendon was the question. Okay. So we did a kind of free body diagram where the height of the ankle really doesn't have anything to do with it. Just kind of threw it in there. And then we drew a free body diagram. So there's the joint, there's the normal force, and then here's the tendon. And then you guys can see that, right? Yeah. Okay. Then we did the sum of the torques. So it'd be the normal force times distance 2, which was 95, minus the
Which one's distance 2 again?
the 95 right here.
Oh, and A is the center where gravity acts.
Yeah.
Okay, I got it.
And then the force of the tendon is the cosine of theta times the distance d. So right there we did the cosine.
Oh, so it does matter then, right? The
No.
height.
No, that's not.
No, that's the force.
Do you want? Wait, what did I say?
You just did F perpendicular. Or F,
Yeah.
F perpendicular times.
The 175?
No,
Oh,
times
no.
2,
Oh,
75.
yeah,
sorry.
you're right, yeah. Okay, so that's fine.
And then we just solved for the force, and that's what we got.
Oh.
Minus because the 75's on the other side.
It causes it to be a positive torque.
Yeah.
Nice. Spider-Man, so you got DC and Marvel represented usually. That's good. Yeah, just put it there and then you guys can take pictures of it. It's a good statics problem. Okay, you guys. Maggie and Morgan. Talk. We'll go this way and then we'll go to shape.
We should pass that around the class so people can take pictures of it so they don't have to print afterwards.
And they get distracted while they're listening.
For like 1 second.
All right. Okay, we'll pass. Okay, Travis had a suggestion which we'll do, but we'll have to have this back. We'll pass it around the class and you guys can take pictures.
Okay.
Okay, so ours is simple. We're just trying to find K when mass equals 0.05 and then the average time is 7.0375.
So what's the problem?
To find K.
But what's this?
What kind of problem?
What kind of problem is it?
Physics.
Okay.
Spring?
It's
It's a spring.
It's a, yeah.
Keep finding Hooke's law, remember?
Yeah,
Yes, yeah.
it is. Yeah.
Okay, anyway. So,
Yeah, okay.
Yeah. it is oscillation. Okay, so you derive your equation to find K. And then you know the average time, so you have to find big T, which is that second line. And then you sub that in and find K.
Okay. That's a simple harmonic oscillator problem. Okay, yeah. All right, we'll go down here. How about you guys?
How is that simple harmonic if it's,
That's what I
oh,
think.
okay.
It's oscillating on a spring, simple harmonic.
Okay.
Hooke's law is just the fact that
K.
that force is proportional to the distance
Oh, okay.
stretched by the spring.
Makes sense.
We can zoom out if you want.
This is just kind of a simple projectile motion problem. Got a cannonball that's fired horizontally off of a pedestal, and it's 1 meter tall. It shoots at 200 meters per second. So, two questions are: how far will the cannonball go before it hits the ground, and then how far will it go if it's raised another 1.5 meters? So, you just use the R equals velocity square root 2h over g for part A, and then part B, you just use 1.5 meters instead of 1.
All right, everyone, make sense? All right. Over Molly and Jet.
Oh, we went with them.
Oh, you went with them? Oh, yeah. Really?
Yeah.
All right. Jessica?
Car weighing 1.2 times 10 to the 4th newtons rests on 4 tires. If the gauge pressure is the 200 pascals, what is the area of each end type of the road?
This sounds so confused.
Well, by trend standards, it's pretty good.
And then you gotta divide by 4 because there's 4 tires, and you find the area with that equation, rearrange it. And yeah.
All right. We'll pass it around. So, pressure, area, that type of one. Mason?
Okay. I just didn't want to disrupt.
Okay, what if this little fishy cuts?
It's just a standard tension equation finding tension of the cable between masses. The mass of the free weight and the mass of the arm.
So what did you do?
It's, yeah, that's supposed to be meters. You take mass of the arm, which is 20 kilograms, times its length times gravity plus mass 2 times center point, which times gravity.
Wouldn't
They should be switched.
Yeah, wouldn't L2 be the full 110 meters,
Yeah.
and L1
The mass
would
of
be
the arm.
5 meters because the
The center of
force
it.
on the arm acts at the center of the arm. Makes sense.
Yeah.
And yeah, then it divided by the full length and the angle of the cable.
Yeah. Okay.
So the distance, so just mixed up.
Yeah.
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 If you take the beam, it's the center mass. The hanging mass should be the holy weight.
Yep,
The hanging, okay,
Yeah.
sure.
makes sense.
Mhm.
All right, we'll pass that one around. So the number, you probably can't trust that number.
Yeah.
The number is
No, I changed it.
raised.
All right, but your
The
end-
calculation should be different.
Yeah,
All right, Kevin, you got one? Okay, Samantha.
Yeah. Okay, I just did a vector addition problem, trying to find the overall displacement. So you can make a little story. Drive 60 kilometers north, then turn east 90 degrees and travel 40 kilometers east. Then, I should write better. To take another turn 90 degrees and then travel 15 kilometers north, and then you find the total overall displacement. And so I first drew it just how the story said, but then I didn't like how that looked, so I redrew it as like all the norths going together and then the east going together. So it just looks like a right triangle. And then you solve using the Pythagorean theorem.
All right. Vector addition.
Yes.
All right. There you go. Brittany?
She's going with them.
Marshall.
Oh, there you go. Okay, all your turn. Get to it. This is a big group.
I did a big one, just have fun. I made one, but it wasn't too
Mhm.
Is that a Superman one?
Yeah, it's a Superman. Lex Luthor sub is at a depth of 1,200 meters in the Arctic Ocean. The density of seawater is 1,025 kilograms per meter cubed. Superman punctured a hole in the sub where the pressure is 1.01 times 10 to the 5th pascals. What would the speed of the water be rushing into the sub? So first you have to find the pressure of the water outside of the sub, and then you can use Bernoulli's equation to find the velocity of the water going into the sub.
All right, it makes sense to everyone?
Wait, is outside of the sub not atmospheric then?
It's,
But it's underwater.
yeah, you're down.
Yeah,
you're down
oh, okay.
1200
Oh yeah,
meters
the
in
pressure
water,
increases.
yeah.
Okay.
All right, makes sense?
Yeah.
Good, good. All right, we'll pass that one around.
Yeah. Yeah, outside of the sub and then after that.
And, Marcus.
We had another kinematics problem where a bullet's fired horizontally at 500 meters per second and it's 1.5 meters above the ground. So we solved the y kinematics for time, and then we plugged time into the x kinematics.
So just to get range.
Yep.
Okay. All right, range on horizontal fire. Good. All
Is
right,
ours
so
yours?
you guys already went on that row. There you go.
Alright, ours is a vector problem, vector addition. You find yourself in a Sahara desert, you are completely lost with no technology. Day one, you travel 8 miles, 30 degrees north of east. Then you find a small oasis and decide to camp there for the night. And then day two, you are more tired that day, and you only travel 6 miles, 30 degrees east of north. So A is draw a picture and then find for east and north how far east and north you traveled for each day, And then C, find how far you are from your starting point. And finally, D, what overall direction did you travel? Give an angle with respect to east. So here we drew pictures for, I labeled the vectors for day 1 and day 2, A and B. And then you break them into their components, as you can see right here, with A cosine of theta giving you, and so you can see the X and Y components of each vector, well, distances you traveled. And then once you find that, you can use Pythagorean theorem to find the resultant. R stands for the resultant vector. And then once you find that, so that will be the magnitude.
Wait, were these distances?
Huh?
Were these distances?
Yeah, well, I forgot to put miles in them.
Okay.
But some of them do. Right here you can see there's miles.
Yeah.
I'll put them. But anyway, and then you can find your angle once you have your, so this is the magnitude. We found it to be 13.54, and then here in the X and Y components. Then using tangent, you can find your angle. We found it to be 42 degrees, well, 42.8 degrees north of east.
Makes sense? All right, vector
Yeah, I'll
addition
put
1.
miles on them before I put.
All right. So is that everyone's? At least a couple on the test, okay?
A couple of them only?
Or at least.
Just gotta field the questions out. Just gotta.
Yeah. Whoa, that's good. You can look at yourself.
Mind if I remove this?
Oh, Travis, I will do it.
Okay. Probably good.
Is it recording?
All right. So you remember, we'll do a couple more example problems. So these are good ones that you had. Were there any no thermodynamic problems?
You should give us,
Okay, so we'll, today I think what we'll do is we'll do that problem with the racetrack. The banked racetrack, we'll do one kinematics, I think, and then also one thermodynamics. Okay? And I think that that'll be a fair enough review. And you have the list. By the way, when all the papers come up, I'll need them here at the end of class, all those problems around. Problems that don't get there, I can't put on the test. It doesn't mean steal the hard ones. So, yeah, that's how I would think about it.
yeah, well, I didn't think of that.
That's,
Already given back?
yeah.
Okay.
Okay, so that we had a racetrack problem, we had a racetrack with a radius r to the position of a car going around the racetrack. So circular motion. And if I looked at this racetrack and looked at the car on it, what I would see would be, and this is 20 degrees, right?
Yeah.
What I would see would be a car going that way, along that racetrack on the bank. And we said the coefficient of friction between the car and the tires and the track, we said was 0.9. And this would be static friction if it's not skid. Question is the maximum speed that this could be moving around. All right, so let's go ahead and solve for that. First of all, we're going to draw a free body diagram for this car. What are the, if this is the maximum speed it can be going, it wants to probably go that way. And so friction would oppose that. Which way would friction be pointing at?
Down the track.
So friction would be pointing down the track. Okay, There's a normal force that points exactly up the track. Anything else?
mg pointing down.
Gravity going down. And that's your forces. Now the sum of those forces is going to be equal to MA. And which way does A point here? So if we're moving around in a circle, A has to be pointing towards
yeah.
the center of the circle.
V squared over r.
And it has to have a magnitude of V squared over R. So over here, A has got to be pointing this way. Okay?
So it's perpendicular to gravity, right?
It will be perpendicular to gravity. Yep, it won't be down the track. It's whatever which way it's towards the center of the circle. So if this is at a constant height, the circle would be the center up here, straight horizontal. Okay? And the magnitude of that A is V squared over R. So I can introduce my coordinate system. I'm going to do it backwards just to mess with you guys. The sum of forces in the x direction, I got to think about this a little bit. That will be equal to m v squared over r. That's ma in the x direction. A is v squared over r. And the sum of the forces, well, so the normal force points a little bit in the x direction, right?
Yeah.
So if I split this up into y and x direction, this angle's 20 degrees. I'm going to call this theta. And I know that because if I send this angle to 0, this angle would get sent to 0, right? Same at the same rate. Likewise, this angle here, if I send this angle to 0, this friction force would go to horizontal, right? And so that means this angle has to be theta, that 20 degrees. So if I'm splitting up the forces into the x direction, what part of the normal force is in the x direction?
Sine of 20.
Normal, sine, I'm just going to write theta, okay? And what other force is in the x direction?
Cosine of, like the friction force cosine of theta.
Plus friction force, magnitude of friction, cosine of theta. By the way, how's this friction force related to this normal force at the maximum speed?
Friction equals mu times.
Yeah.
At maximum speed, there's a good relation between this friction and normal force. It's mu n. So I could write this as n sine of theta plus n mu s cosine of theta. So I can say that m v squared over r is equal to the normal force sine of theta plus mu s cosine of theta. Good? All right, let's look at the sum of forces in the y direction. And if this thing's not going up or down the track, what should it be? 0. Okay, MA should be 0 in the y direction if it's not moving up and down the track. And so what's the force? What's the forces in the y direction?
Normal force, cosine theta.
Normal force cosine of theta.
Minus friction force sine of theta.
Minus friction force sine of theta. Minus sign comes in because of that this component of the friction force points in the negative y direction. Anything else?
Minus mg.
Minus mg. Okay, good. So I'm going to substitute in mu s n for this friction force and bring this mg over to here. So I get mg is equal to normal force cosine of theta minus mu s sine theta. You see what I did? Just wrote the friction force mu s n. And then so this would be normal force cosine of theta minus mu s n sine of theta. Factored out the normal force. Okay. All right, now, so I know everything in here, but except for V and N. I can solve for N from here in terms of everything else,
And then plug it back.
and then plug it back in. And I don't know what mass is either, but we'll see if that cancels out in just a second. All right, so N, from the bottom equation, N is going to be mv divided by cosine of theta minus mu s sine of theta. Plug that in for this one. Plug it into 1. And I would get that m v squared over r is equal to m g over cosine of theta minus mu s sine of theta times sine of theta plus mu s cosine of theta. Like that, right? These m's cancel out. If I'm solving for v, I can multiply both sides by r. And I get that v is equal to square root of g r times sine of theta plus mu s cosine of theta over cosine of theta minus mu s sine of theta, that's square root of that. 1/2 power square root. Okay?
So when we do the algebra, is it okay if we if we divided and then multiply by the square root of g over g times r? Like did the sine plus the cosine stuff?
Yeah.
Okay.
Yeah, whichever way you wanna do it, that's correct.
Okay.
You'll get the same thing. And so when I plug in numbers, I got like 1.88 for this. So that was like 1.88 square root of GR or something like that.
Why is there an R right there on the top?
There, because
you
this is
multiply.
mv squared over r,
Uh-huh.
and I multiplied both sides by r. There
Oh,
wasn't an r here.
Okay, the R's not crossed out though, it's just in the equation.
Yeah, that's right.
Okay.
That's g's
then-
tail.
Okay. So V squared, okay. And we're solving for V, right?
Yeah. Okay, does that make sense to you guys? And so you get something like this as your maximum speed. So it depends on the racetrack. So that's kind of a good circular motion one.
Why did you have g r squared root by 1.88?
This number, if I plug in 20 degrees here and 0.9 here, I mean, I worked it out and I got something like that.
Oh, that times that. Okay.
Yeah.
Gotcha.
Now maybe I didn't take the square root, I don't remember.
Okay.
Okay, ready for the next one?
Mm-hmm.
Is there gonna be one that's that complicated on the test?
Possibly.
Maybe.
Oh. You told me yesterday no.
This will probably be a little harder, that's why. But if you can do this one, you should be able to do anything on the test. Another circular motion one would be like a roller coaster, where you gotta figure out the speed before it falls off. Remember, the condition for it falling off is that the normal force goes to 0. Okay. All right, let's do a thermodynamics one. And then a projectile motion one. So, but probably the most likely thermodynamics type problem would be putting one object in another object, like a beaker of water. Say I have maybe 10 liters of water, so 10 kilograms. At maybe 30 degrees C. And then maybe place 1 kilogram of iron at 100 degrees C, specific heat of iron, that's little c, is 0.11, wait, 0.44.
Yeah.
Roughly joules per,
I thought that was kilojoules.
yeah, kilojoules per kilogram. Joules per gram is the same thing as kilojoules per kilogram. Degree C. Okay? And then specific heat of water
4.1.
equals 4.1, full round.
4.19.
So the question might be, if I place this iron at 100 degrees here in this water, what's the final temperature? Make sense? Or maybe I might do it with an ice cube, in which case you'd have to use the latent heat of melting.
So if you do the an ice,
Fusion, yeah.
like if you, so you do that plus the regular stuff we've been doing, right? Like you have to melt it before.
Well, you just take the total heat lost
Mhm.
by 1 has to be the total heat gained by the ice
Right.
cube. So you have latent heat of melting, and then also to raise that temperature, that little bit of water that melted to final temperature. Okay, so what's the condition? So what? How do you start this one?
Q1 equals negative Q2.
All right, so you would make sure that kind of label these things. So I'm going to call that T1, T2, and then we know that heat's being lost by T2 into T1. So I'm going to say that Q1 is equal to negative Q2. Now that's always heat gained by 1 would be equal to the
Loss.
negative of the heat gained by 2, so it's losing heat. Make sense? Okay, and so this thing, pretty easy formula for these Q's. You just take mass 1, specific heat of 1, change in temperature of the first quantity is equal to minus the mass 2, C2, change in temperature 2. Okay, where T. Now these things keep changing until they get to a final temperature, and they'll have the same final temperature. All right, and so the final temperature in both of these would be TF. So I could write M1 C1 TF minus T1 is equal to minus M2 C2 TF minus T1, or T2. Okay?
You should give us a problem with the ice cube one, because this one, not hard.
Well, the ice cube one's not hard either. We'll do, okay, Q1.
The ice cube one is just, they all have the same.
You just have the Q's slightly different. We will do an ice cube one. Okay, so if I'm trying to solve for the final temperature, I could do, I'll just combine everything with T final in here together. So here I have a minus M2C2 T final, so I bring that over to this side. Is equal to, and then everything else I'm going to put on the other side. So I have a M2C2 T2 here, and then I have a plus M1 C1 T1 here. See that?
Mhm.
I can factor out a T final from both of these terms. So I could do M1 C1 plus M2 C2 times T final is equal to M2 C2 T2 plus M1 C1 T1. Divide through by this T final. M1 C1 plus M2 C2. Then plug in numbers. So, you know, that would be T1's 30, T2 is 100. And so I'd get M2 would be 1 times 0.44 kilograms. T2 would be 100 plus 10 times 4.19 times 30, all over 1 times 0.44 plus 10 times 4.19. And you just plug in and then you get a final temperature. Make sense? So that's one. Let's do the ice one. Let's say instead of iron, I had ice at 0 degrees Kelvin, or not Kelvin, C. And let's say that I had 0.1 kilograms, so 100 grams of ice. Let's see what the final temperature would be.
And then what about, the water is all the same?
10 kilograms of water, right?
What's that?
The water.
Yeah, water's the same.
Okay.
10 kilograms, 30 degrees. Now, what was the specific heat of latent heat of fusion?
That's 0.1.
I'd have to give this to you. 0.1 kilograms. So the latent heat of fusion of ice is 334 kilojoules per kilogram. So that means it takes 334 kilojoules to raise to change 1 kilogram of ice to water. Does that make sense? They'll both be at freezing point. So I'll start out in the same way.
Do we need
Q1
a
is equal to minus Q2. That's the fundamental physics.
Do we need the specific heat of ice?
Because it's at 0 degrees
Okay.
C, so we're not raising the temperature of the ice at all.
Okay.
We're just melting it and then raising the temperature of the water.
Okay.
Make sense?
Lowering. Aren't we lowering the temperature of the water?
What's that?
Aren't we lowering the temperature?
Yeah.
Yeah.
You add ice to it.
All right, so here's what we're gonna do. Q1, we're gonna call it still the water. We're still gonna have this, everything related to the ice, T2 is 2. So the heat that is gained by the water, or that is lost by the water, Q1 is equal to specific heat of water. Maybe I'll do CW for water, times mass of the water, C1. And then I get T final minus T1, okay? Now this is losing heat, so this T final will be lower than T1. Q2 would be the amount of heat that's gained by the ice. First of all, it would be, if we have to melt the ice, it would be L, ice, times mass ice. And then plus see, plus C1 or C2, M2, M ice,
So we do need the C.
times T final.
Yeah, but at that
minus
point
0
it'll be
degrees.
water.
So you just use the other water.
Yeah,
Oh.
C2 will be just the same one as water, right?
Okay.
I'm gonna call, so I can call that C1. It'll be confusing, but it's the same C. You melted the ice, now you have to heat the ice up to the final temperature. Okay, now just plug that into the Q1 as minus Q2. C1, M1, Q final, minus C1, M1, T1, that's Q1, minus Q2, so minus L ice, M ice, minus C1, M ice, T final. Combine everything with the T final. And then everything without the T final you put on the other side. So I get C1, M1, T plus C1, M ice, T final, is equal to minus L ice plus C1, M1, T1. L ice, M ice. And then if I want to solve for T final, I'll just divide by that. Where C1 says specific heat of water. Okay. Then you just plug in numbers. So 30 degrees, 10 kilograms, 4.19 kilojoules per kilogram. 0.1, 330, whatever. And then these things here. Make sense?
Yeah.
All right, I'm gonna need those things up here, okay?
And M2 is the same as the M of the ice, right?
Yeah.
Monday at 8:30.
I don't think this is quite all of it yet.
Got a couple here left.
Monday, 8:30. This is.
Oh,
That's active.
Monday, 8:30. See you here.
Same time.
8:30. Yep. Same time.
no, I'm fine.
Just stop that. Let's get
Wait, I missed a place.
Oh, the library. All right, cool.
Are you on your way?
Yeah. Nothing else to do. In fact, that is what I have to do.
Divided by your 7.
What's that?
Divided by your 7 comes out to like 16